What if I told you a fully working electric motor could be printed flat on something as simple as a circuit board? No spinning coils, no bulky housing, no traditional design. Just layers of copper traces etched onto a PCB, and somehow it spins. Not only that, it challenges everything engineers thought they knew about how motors should be built. This isn't science fiction. This is real technology, and it could completely change the future of machines. For more than 100 years, electric motors have followed the same basic formula. You take coils of wire, you add magnets, you generate a magnetic field, and something rotates. That principle powers almost everything around us. Your ceiling fan, your washing machine, your electric toothbrush, your laptop cooling fan, even electric cars. The design evolved over time, but the core concept stayed the same. Until now. Because engineers have created something radically different. A motor that doesn't need bulky windings. A motor that can be manufactured like electronics. A motor that can be printed directly onto a board. To understand why this matters, first imagine a normal printed circuit board. The green board inside your phone or computer. Its job is usually simple. Connect chips, carry signals, deliver power. But in this new design, the board does much more. The copper traces are arranged in precise circular patterns. When electricity flows through those patterns, they create magnetic fields. That means the circuit board itself becomes the motor stator, the part responsible for generating motion. Then a lightweight rotor is placed above it. Sometimes it contains tiny magnets. Sometimes it uses other magnetic materials. As the current switches through different traces in sequence, the magnetic field rotates. And when the magnetic field rotates, the rotor follows. That means movement from a flat board. No wound copper coils. No giant metal code. No heavy assembly. Just smart engineering. And this is where things get wild. Traditional motors require many manufacturing steps. Wire winding, assembly, balancing, housing installation, testing. Each step costs time and money. But PCB motors can be manufactured using processes already used in electronics production. That means they could be faster to make, cheaper at scale, more precise, and incredibly compact. Imagine designing a motor in software, then sending it to production the same way you'd manufacture a motherboard. That changes everything. Because once motors become flat, new possibilities open up. Think about drones. Every gram matters. A lighter motor means longer flight time and better efficiency. Think about robotics. Thin motors could be built directly into joints and moving surfaces. Think about laptops and compact devices. Cooling systems could become slimmer and quieter. Think about medical tools. Small precision motors could power advanced instruments where space is extremely limited. Even wearables could benefit. Imagine smart devices with tiny moving mechanisms built directly into their electronics. This is the kind of innovation that creates entirely new product categories. But there's an important truth. This technology is impressive, but it is not magic. PCB motors still face serious limitations. The first is torque. Traditional motors are excellent at producing strong rotational force. PCB motors are usually much weaker. That means they're not ideal for heavy-duty machines. The second challenge is heat. Thin copper traces can only handle so much current. Push too much power through them, and temperatures rise quickly. The third issue is efficiency. Lose more energy compared to optimized conventional motors. So no, you won't see one replacing a factory motor tomorrow. You probably won't see one towing a truck anytime soon either. But that misses the point. Every revolutionary technology begins with limitations. The first computers filled entire rooms. Now they fit in your pocket. The first electric vehicles were slow and impractical. Now they compete with supercars. The first smartphones looked unnecessary. Now they run modern life. New ideas often start weak, expensive, and underestimated. Then they improve, and improve again. That's why PCB motors matter. They introduce a new direction, a new way of thinking about motion itself. Instead of treating motors as separate mechanical parts, what if movement becomes part of the electronics? What if the board inside a machine doesn't just control the system? What if it is the system? That could reduce parts, reduce weight, reduce cost, increase reliability, and make products easier to build. In the future, engineers may create machines where motors are invisible, built into surfaces, embedded into frames, hidden inside thin layers of electronics. Imagine foldable robots, ultra-thin automation systems, smart appliances with silent internal motion, compact medical devices with incredible precision, or consumer products we haven't even imagined yet. That's how disruption works. At first it looks like a curiosity, then it becomes useful, then suddenly it's everywhere. And maybe the most fascinating part of all this is what it teaches us. Some technologies feel permanent. They feel finished, like no one can improve them anymore. But history keeps proving the opposite. Even something as old and familiar as the electric motor can still be reinvented. So the next time you look at a simple circuit board, remember this. It might not just power a machine. One day, it might become the machine. If you enjoyed this video, subscribe for more breakthrough technologies changing the future. Because the next invention that looks impossible today could be normal tomorrow. And that future may be closer than most people realize. Right now, engineers around the world are racing to make machines smaller, lighter, smarter, and more efficient. Every gram saved matters. Every millimeter of space matters. Every extra component removed matters. That pressure is exactly why inventions like PCB motors are gaining attention. Because when industries hit physical limits, they start rethinking everything. Take drones, for example. Modern drones depend on motors that are powerful, but still bulky compared to the electronics controlling them. Now imagine stabilization systems, camera gimbals, microfans, or precision steering mechanisms powered by flat-printed motors built directly into the frame. That could mean lighter designs, longer battery life, better balance, and more room for sensors or payload. Now think about robotics. Most robots today rely on motors connected through gears, belts, shafts, and housings. But what happens when movement can be integrated directly into limbs or surfaces? A robotic hand could become thinner. A moving panel could become faster. Small service robots could become quieter and more elegant. Instead of building around motors, designers may build motors into the design itself. That is a major shift. Then there's the world of consumer electronics. Phones became thinner. Laptops became lighter. Wearables became smaller. But moving components still take space. Haptic systems, mini cooling fans, camera mechanisms, tiny actuators. All of these rely on traditional mechanical parts. PCB-based motion systems could change how those devices are designed. Imagine a laptop with ultra-thin silent cooling. Imagine foldable devices with embedded motion components. Imagine gaming controllers with advanced tactile feedback systems built directly into the internal boards. And then comes medicine. One of the biggest challenges in medical engineering is precision in tiny spaces. Surgical tools need reliability. Portable devices need compactness. Assistive devices need low weight. Printed motor systems could help power miniature pumps, precise adjustment mechanisms, compact scanners, or next-generation wearable health devices. When space is limited, every innovation counts. But perhaps the most exciting part is customization. Traditional motors are standardized. You choose from existing sizes, shapes, and ratings. Then you design your product around them. But with PCB motors, that process could flip completely. Need a circular motor? Design it. Need a square one? Design it. Need a motor shaped to fit around sensors, batteries, or structural parts? Design it. because now motion becomes something engineers can customize digitally. That means products no longer adapt to motors. Motors adapt to products. That could unlock designs never before practical. However, there is still one giant challenge standing in the way: power. The world loves small devices, but it also demands performance. People want stronger drones, faster tools, more powerful robots, longer battery life. And delivering high power in ultra-thin printed systems remains difficult. That's why researchers are experimenting with better materials, thicker copper layers, improved cooling methods, smarter control electronics, advanced magnetic designs, hybrid systems that combine printed stators with premium magnetic rotors. Each improvement pushes the concept forward. And sometimes, progress happens quietly. No headlines, no giant announcements. Just better prototypes, better efficiency, better reliability. Then one day, a product launches using it. And most people never realize a hidden revolution just happened. That's how technology usually changes the world. Slowly at first, then suddenly. Years ago, touchscreens felt futuristic. Wireless earbuds felt impractical. Electric cars felt niche. Now, they're normal. So ask yourself this: if engineers can turn a flat circuit board into a working motor, what else are we assuming is impossible? Could batteries be reimagined? Could speakers be printed into surfaces? Could robots become thin as paper? Could machines someday be manufactured almost entirely through automated printing processes? Those questions sound wild today, but so did the idea of a motor printed on a PCB. And that's why breakthroughs like this matter. They don't just create products. They expand imagination. They remind us that the rules we accept are often just habits of the past. Because physics wasn't broken. The old design assumptions were. And when assumptions break, innovation begins. So the next generation of machines may not look mechanical at all. They may look smooth, minimal, silent, flat, intelligent, with motion hidden inside layers of circuitry. No visible motor, no obvious machinery, just performance. That is where engineering is heading. And if this technology continues improving, the machines of tomorrow may be built less like engines and more like computers. If you enjoyed this journey into future tech, hit subscribe and stay tuned, because the next invention rewriting the rules might already be in a lab right now. And somewhere in that lab, an engineer is probably staring at a prototype that looks completely ordinary. A thin board, some copper traces, a few components, maybe a small spinning disc. Nothing dramatic. Nothing that looks like it could reshape industries. But history is full of inventions that looked unimpressive in the beginning. The first semiconductor chips were tiny and weak. The first digital cameras had terrible quality. The first electric vehicles were dismissed. The first 3D printers were slow curiosities. Then the technology matured. And once it matured, everything changed. PCB motors may be walking the same path. Because the real strength of disruptive technology is not what it can do today. It is what it becomes after 10 years of iteration. Imagine version 1. It works, but modestly. Version 2 becomes more efficient. Version 3 gets cheaper. Version 4 enters consumer devices. Version 5 reaches mass production. Version 6 becomes so common that nobody talks about it anymore. That cycle has repeated again and again across modern history. And it often begins with people saying, "That will never replace the real thing." But replacement is not always the goal. Sometimes the smartest technology doesn't replace. It creates a new category. Cars did not replace trains. Smartphones did not replace computers. Streaming did not erase cinema. They changed behavior by creating new options. PCB motors may do the same. Instead of replacing every conventional motor, they could dominate areas where traditional motors were never ideal. Places where size matters. Places where weight matters. Places where silence matters. Places where cost matters. Places where integration matters. That list is longer than most people realize. Think about smart homes. Hidden vents adjusting airflow. automated blinds with nearly invisible movement systems, quiet locks, micro-positioning devices inside appliances, compact pumps, precision dispensers. Now think about transportation. Active aerodynamic surfaces, sensor alignment systems, lightweight interior mechanisms, adaptive lighting modules, tiny cooling systems, self-adjusting components hidden throughout a vehicle. Then think even bigger. Factories, warehouses, agriculture. Thousands of small automated actions happen every second in modern industry. Many of them need motion. Not massive motion, small motion, repeated motion, reliable motion. That is exactly where unconventional motors can become valuable. Because the future is not only built from giant machines, it is built from millions of tiny systems working together. And the smaller those systems become, the more important compact actuation becomes. That's why engineers obsess over things most people never notice. A few grams saved, a few cents reduced, a few millimeters removed, a few watts improved. Those tiny gains can transform an entire product when multiplied millions of times. So when someone sees a PCB motor and says, "That thing is weak," they may be asking the wrong question. The better question is, weak compared to what task? Because a jet engine is weak at powering a wristwatch. A watch battery is weak at moving a train. Technology only makes sense in context. And context is where PCB motors become interesting. Imagine a future smartwatch with silent internal mechanisms. Imagine eyeglasses with micro-adjusting optics. Imagine health devices that automatically calibrate themselves. Imagine ultra-thin educational robots for children. Imagine foldable keyboards with moving tactile systems. Imagine drone swarms using dozens of lightweight printed actuators. These are not fantasy concepts. They are the kind of use cases engineers actively chase. And once one profitable application succeeds, investment follows. Then competition begins. Then innovation accelerates. That is when progress moves fast. You'll see startups promising breakthroughs, major manufacturers filing patents, universities publishing new designs, materials companies developing better substrates, control chip makers optimizing driver systems. And suddenly, a strange little motor on a board becomes an ecosystem. That is how industries are born, quietly, one prototype at a time. Another fascinating possibility is modular manufacturing. Today, many products require sourcing motors from specialized suppliers. Those motors must fit, must ship, must be assembled, must be tested separately. But if motion systems can be printed as part of electronics manufacturing, supply chains can simplify. Fewer separate parts, fewer assembly stages, faster production cycles, more local manufacturing options. That matters in a world where supply chains can break overnight. And then there is software. Modern hardware increasingly depends on software-defined behavior. Cars receive updates, cameras improve after purchase, machines optimize themselves, become tightly integrated with electronics. They become easier to tune, monitor, and personalize through code. Imagine buying a device that physically improves through firmware updates. Stronger response curves, quieter movement, better efficiency, smarter precision. That line between hardware and software keeps fading. PCB motors fit directly into that trend, because they are mechanical in function, but digital in philosophy. Designed on screens, simulated in software, manufactured like electronics, controlled by code. That combination is powerful, and it suggests something deeper. The future may not separate machines into categories like electrical, mechanical, and digital. Those boundaries may merge. Products will simply be systems, integrated, adaptive, compact, smart. And when that happens, many old components will be reinvented from scratch, motors included. Of course, there will be failures too. Some designs won't scale. Some companies will overpromise. Some prototypes will never leave the lab. That's normal. Every technology boom includes dead ends. But even failed experiments move progress forward. They reveal limits. They inspire alternatives. They teach engineers what to fix next. So never mistake early imperfections for final potential, because what looks crude today may become elegant tomorrow, and what looks niche today may become invisible infrastructure tomorrow. The world runs on technologies most people never think about. Bearings, sensors, connectors, converters, microcontrollers. The greatest inventions are often the ones users never notice. PCB motors may someday join that list. Inside products. Working silently, doing their job, taken for granted. And if that happens, it means they succeeded. Because true technological victory is not always fame. Sometimes it is becoming so useful that nobody can imagine life without it. So the next time you hear about a weird prototype that seems too small, too strange, or too weak to matter, pay attention. That's often exactly how the future begins. Not with a giant machine, not with a dramatic explosion, not with instant perfection, but with a quiet spin on a printed board. And that quiet spin may represent something far bigger than a motor. It may represent a shift in how humanity builds technology itself. For most of modern history, machines were created by combining separate parts: a motor from one supplier, a controller from another, a housing from another, gears, brackets, fasteners, wiring, cooling systems, each component designed independently, then assembled into one product. That method built the modern world, but it also creates friction. More parts mean more cost, more assembly means more time, more suppliers mean more complexity, more moving pieces mean more failure points. Now imagine a different future. A future where functions merge together, where structure, intelligence, and motion are designed as one system from the beginning. That is the philosophy behind many next-generation technologies. And PCB motors fit perfectly into that mindset. Because instead of adding a motor afterward, you can design motion directly into the product. That sounds subtle, but it changes how engineers think. Instead of asking, where do we fit the motor, they ask, how do we shape the whole system? The product, so movement is built in. That one change can unlock radical designs. Picture a smart desk with hidden mechanisms that raise, lower, tilt, and adjust without bulky hardware underneath. Picture wall panels that open silently using embedded motion systems. Picture medical beds that become thinner, smarter, lighter, and easier to clean. Picture aircraft interiors where small adjustments happen through flat internal systems instead of heavy assemblies. Picture satellites where every gram saved matters more than gold. When weight is expensive, compact motion becomes priceless. And that leads to one of the most important industries of all: space. Every kilogram launched into orbit costs money. Every cubic centimeter matters. Every point of failure is dangerous. That's why aerospace engineers love compact, lightweight, highly integrated systems. PCB-based motion solutions could someday help with sensor alignment, valve control, cooling systems, deployment mechanisms, antenna positioning, or countless micro-adjustments. In space, elegant engineering wins. Then there is defense, research, and exploration. Remote robots in dangerous environments, underwater systems, hazardous inspection machines, portable science equipment. Anywhere size, reliability, and precision matter, engineers search for better motion systems. And sometimes the best solution isn't bigger, it's smarter. That lesson appears everywhere in history. Bigger computers lost to smaller chips, heavy cameras lost to digital sensors, large maps lost to smartphones. Powerful systems often become compact systems. Compact systems often become dominant systems. So, when people laugh at a tiny printed motor, they may be watching the first chapter of a familiar story. Another reason this matters is education. As motors become easier to prototype, students and inventors gain access. Traditional motor development can be expensive and specialized, but PCB tools are already used by startups, hobbyists, universities, and makers around the world. That means future engineers may experiment with motion the same way they already experiment with electronics. Design it on a computer. Order a board. Test it. Improve it. Repeat. When innovation becomes accessible, breakthroughs multiply. Some of the best ideas won't come from giant corporations. They'll come from small labs, garages, university dorm rooms, independent creators. That's how revolutions often spread. Not top-down, bottom-up. Thousands of minds solving different problems at once. And each improvement compounds. One team improves cooling. Another improves magnetic materials. Another writes better control algorithms. Another reduces manufacturing cost. Another discovers a niche market. Together, progress accelerates. Then suddenly the technology is no longer experimental. It is practical. And once something becomes practical, markets move fast. Investors pay attention. Competitors react. Factories adapt. Consumers benefit. But perhaps the most powerful effect is psychological. Breakthroughs like this remind society that mature industries are never truly finished. People assume motors are solved. People assume batteries are solved. People assume transportation is solved. Then someone challenges the assumption, and progress resumes. That mindset matters beyond engineering. Because stagnation often begins when people believe nothing can improve. Innovation begins when someone refuses to accept that. The printed motor is a symbol of that refusal. It says, why must motors be bulky? Why must coils be wound by old methods? Why must motion remain separate from electronics? Why not redesign the entire idea? Those questions create the future, and the same thinking could reshape countless other fields. Buildings with active materials, furniture that self-adjusts, entire systems reimagined, all from the same willingness to ask, what if we started from scratch? That is the mindset that drives real breakthroughs. Adjusts. Clothing with adaptive components. Factories with self-reconfiguring tools. Consumer devices with almost no visible mechanics. Machines that feel less like machines and more like living systems. Responsive, silent, adaptive, integrated. That is where technology trends are heading. Not just stronger machines, smarter machines. Not just bigger systems, more elegant systems. Not just more components, fewer components doing more work. PCB motors may be one small piece of that puzzle, but small pieces can trigger huge change. A transistor was small, a microchip was small, a sensor was small, yet each one transformed civilization. Scale can be deceptive. Sometimes the smallest parts carry the biggest consequences. So maybe one day, children will open an old device containing a conventional motor and laugh. They'll wonder why machines used to need so many parts, why motors were so thick, why movement required so much hardware. Just like we look back at giant computers and floppy disks today. That is how fast normal can change. And if that day comes, it will begin with moments like this. A strange invention, a skeptical audience, a prototype that seems minor, and a few engineers who kept improving it anyway. Because the future rarely arrives looking powerful. It arrives looking unnecessary, until suddenly it becomes essential. And maybe that's the real lesson here. The technologies that change the world rarely arrive looking impressive. They begin small, they begin strange, they begin underestimated. A quiet spin on a printed board today could become the foundation of tomorrow's machines. So the next time someone says innovation has slowed down, remember this motor. Because the future isn't always loud. Sometimes it starts with a whisper of motion. If you enjoyed this video, subscribe for more breakthrough technology stories shaping tomorrow. And trust me, the next impossible invention is already on its way.